Find a video that explains evaporation better than this one. Be one of the first 3 people to email us the proof, and we will give you $100. That is how sure we are about the quality of our explanation. This video is made so clearly that even a child between 5 and 8 years old can understand it. And we make that same bet in every single video on this channel. What you were taught in school, and in fact what is still taught in school today, is wrong. You are taught evaporation, not evaporation. Watch this video and then politely go tell your teacher to update the textbooks. The explanation in this video is so easy that a 7 or 8-year-old can master it and even teach it. You will learn 5 other things I bet you $100 you didn't know about fluids. For instance, we all know you can map land, but did you know that water, all fluids in fact, have maps too? Even the water in your bucket has a map. And did you also know that whenever you look at any body of water, from oceans and rivers to the water in your cup of tea, what you're looking at is just a fraction of the real water, and that the other bigger part is invisible? Well, what say you, little one? Should we keep all these enchanting secrets to ourselves? You were told that evaporation is simple. They told you that evaporation happens when water molecules reach a certain speed and then leave the water, becoming vapor. That explanation is wrong, and it is wrong because it misses the whole point. Why? Because in the very same breath, they also tell you that there must be equilibrium between water molecules in the liquid and water molecules in the air. And the moment they say that, the real question appears. The real question is not, can some water molecules move fast enough to break away? The real question is, how does net evaporation continue if equilibrium keeps preventing it from happening? Put simply, equilibrium dictates that for every water molecule reaching breakaway speed, the speed required to leave the water and evaporate, a vapor molecule must move in the opposite direction and become a water molecule. So in reality, equilibrium is the enemy of evaporation, yet evaporation still happens. So how does your teacher explain that? That is the whole point. If your explanation does not explain how evaporation keeps going despite equilibrium, then you did not explain evaporation. You skipped the very thing that matters most. Now, we are not claiming a new law of physics. We are not claiming we discovered some secret dragon hiding under your kitchen pot. What we are saying is this: the important pieces were already there, but they were not being shown clearly enough for people to truly understand what is going on. So today, we are going to rebuild the picture properly. And here it is. There are 2 very important things you need to know about evaporation. But before those 2 things, there is thing 0. Here comes thing 0. Evaporation is not water going into a vacuum. It is not water jumping into empty nothingness. It is not a molecule of water flying upward into some magical free parking lot in the sky. No. Evaporation is a story about interaction. It is a story about water in the liquid interacting with water already in the air. Yes, there are other gases in the air too. But the heart of the story is this: water in the liquid is interacting with water vapor in the air right above it. And that air above the water is itself interacting with the surrounding lateral air. So evaporation is not one lonely jump. It is a tug of war between 2 water regions, liquid water and vapor water. That is thing 0. Miss thing 0, and the rest becomes nonsense very quickly. And do we like these nonsense glasses? So lock this picture into your mind. Evaporation is the story of liquid water doing battle with vapor water, and most of the time, it is a draw. Nobody wins. We will tell you what makes liquid water win shortly. But you need to carry this picture with you at all times. Whenever you see open-air water, you must understand that you are barely looking at the visible part of water. Because in open air, there is always invisible water, vapor, sitting on top of liquid water. Always. So the next time you look at the ocean, a river, water in your pot, or water in your cup of coffee, just know this: its enemy, vapor water, is sitting right on top of it, putting pressure on it, preventing liquid water from evaporating. Maybe because evaporation is not a good thing if you're a planet. What would you become if all your water broke free, broke away, and went flying into space forever? So remember, whenever you see liquid water, its archenemy is sitting right on top of it, preventing it from evaporating. Now let us move to thing 1. Thing 1. The first thing you need to appreciate is the Maxwell-Boltzmann distribution curve. Do not panic because we used a fancy name. It is very straightforward. In any big group, you usually have 3 broad kinds of individuals: slower ones, average ones, and faster ones. Water molecules are like that too. Inside water, not all molecules move at the same speed. Some are slower, some are average, some are faster. Now here comes the first thing I bet no one has ever told you. That curve is not just some abstract graph floating in textbook space. To understand evaporation, you should flip that curve 90 degrees counterclockwise and dip it into the water. That is thing 1. When you do that, the curve becomes a probability map, a numbers geography, a map of where molecules of different speed classes are most likely to be found in the greatest prevalence. There is a link in the description for any physics nerd who wants to know more about this. Call it numbers geography since molecules are split into rows, and each row contains molecules of the same speed class. If you had a speedometer and pointed it into most water bodies, you would actually see something like this. It is a probability map. We are not saying that all water molecules within a row have the exact same speed. We are saying something sharper, that the probability of finding water molecules of the same speed corresponds almost 1-to-1 with the Maxwell-Boltzmann distribution curve flipped 90 degrees counterclockwise. So now, the slow end of the curve is deeper in the water. The middle section sits in the middle, and the fast end sits near the surface. Why? Because the temperature structure of the water gives you a structure of typical kinetic scale with depth. In plain English, the local thermal state of the water changes which motion scales are most typical in each layer of the water. So when we flip the curve and dip it into the water, we are turning a probability overspeed picture into a where most likely picture inside the water. This does not mean each molecule has a permanent apartment number and never moves. It does not mean nature runs a tiny bureaucratic filing cabinet where the slow molecules live downstairs forever and the fast molecules rent penthouses. It means this is a probability map of prevalence, a map of where slower, average, and faster molecules are most likely to be found in the greatest concentration under the water's real, depth-dependent thermal structure. That is why this move is not just a cute teaching cartoon. It is a representational map. Those glasses see a cool map yet? If the water is colder, you will typically have a much larger slow-speed population deeper down, then a middle group, then a smaller fast group near the surface. And this is why even cold water can still evaporate. Because even in colder conditions, thanks to thing 0, water vapor molecules that always sit on top of your liquid or ice water bounce on and off it, imparting speed to it, and therefore, there are still some molecules in the fast tail. Most explanations stop here. They say, see, some molecules are fast enough, therefore, evaporation. No, that is wrong. Because it misses the whole point. Because thing 1 alone does not solve equilibrium. Thing 1 tells you which liquid water molecules are in the best position to break away, but it does not tell you that there is a fight. And vapor water in the air does not want liquid water to break away and occupy its place. Vapor water is no pushover. Whenever you increase the temperature of the liquid, vapor water recruits even more vapor water molecules, and resistance, which we call pressure, increases. making it even more difficult for liquid water molecules to break away. That is why you need Thing 2. Thing 2. Just as we flipped the distribution curve 90 degrees counterclockwise and dipped it into the water for Thing 1, we must now place the distribution curve on the sideways edges of the water container and the lateral air region around it. This is the missing move. This is the move most people leave out. And once you leave this out, you miss the whole point of evaporation. In Thing 1, the curve helps us understand the probability geography inside the water. In Thing 2, the curve helps us understand the removal geography in the lateral air around the water. So now, picture the air in two parts. First, there is the air right above the liquid water, fighting to prevent liquid water from escaping and becoming what it itself is: vapor. Call that the haters team. Second, there is the lateral surrounding air on the sides and beyond. Call that the sideways team, the sideways tug-of-war team. Now, here is the key. The haters team is where vapor already in the atmosphere has been living for ages, including newly formed ones. That is where the crowd forms. And that crowd of haters gets bigger and heavier when temperatures get warmer, because it must prevent evaporation. They're haters, after all. That is their #1 goal in life. That is what we call equilibrium. Their whole job is to push back. The haters team is literally the no evaporation allowed team. So what must happen? They must be cleared away sideways into the surrounding air. Literally. The sideways tug-of-war team lines up from strongest on the outside to weakest on the inside, and even its weakest member is stronger than any vapor molecules in the haters team. So they form a chain, and they pull the hater vapor water molecules out of the way, one by one. And by doing that, they free seats in the haters team, one by one, for breakaway liquid water molecules to leave the water while equilibrium is conserved. That is why in Thing 2, we place the distribution curve on the sideways air edges. It is literally a line being pulled. Its weaker pullers are right next to the side of the water, its much stronger pullers are farther out, and they too can recruit more or less, but not based on temperature, based on ventilation, meaning you speed up molecules mechanically rather than with heat. Thing 2 is how evaporation gets past equilibrium strongly enough for net evaporation to continue. That is the whole point. Without free seats in the haters team, there is no evaporation, so now the machine becomes clear. Thing 0 explains that whenever you see liquid water, there is always its alter ego, the hater, vapor water, sitting right on top of it, both imparting speed to it and, most importantly, preventing it from evaporating. Thing 1 explains the probability geography inside the water. Thing 2 explains the clearing geography, the pull-away line, in the lateral surrounding air. Why this matters in real life. Now test this in the real world. Take the same quantity of water and place it in 4 different situations. Spread out on the floor, in an open container, in a closed container, and deep down in a very deep well. Keep them in the same room. Wait. You will notice that the water on the floor disappears fastest. Why? Because it is very exposed, and the near-surface vapor can be cleared more easily into the surrounding air because the pull-away line has lots of room to work its magic. The open container also evaporates, but more slowly because the pull-away line can only pull at the surface. In the closed container, there is no evaporation at all because the air above the water gets humid and stays trapped. No pull-away line is present. And in the deep well, there is almost no evaporation because the pull-away line has almost no room to work its magic. So the difference is not just how many fast molecules exist. The difference is how big can your pull-away line get, and how fast can it get big. That is why Thing 2 matters so much. One last thing before we go. Did you know that when water boils in open air, its temperature stays at about 100 degrees Celsius or 212 degrees Fahrenheit as long as liquid water is still there? Boiling happens when water's vapor pressure finally matches the surrounding atmospheric pressure, and at sea level, that happens at about 100 degrees Celsius. Why? Because the most gangsta showdown happens on both sides. As the water gets hotter and starts approaching its boiling point, it is no longer just trying to sneak a few molecules out from the surface. Now it has to fight the pressure of the whole atmosphere pressing down on it. That is why boiling is not just faster evaporation. It is the moment water becomes strong enough to make vapor bubbles inside the liquid itself. So nature says, "You want out? Then beat all of me." Instead of one defense line, you get all the lines going from the one in front of you all the way to the limits of Earth and space. They all muscle up and block you from evaporating. And liquid water says, "Fine, I won't wait for the surface anymore." Instead of only forming vapor at the top, water starts making vapor inside itself. That is why boiling water makes bubbles from within. Those bubbles are pockets of water vapor forming inside the liquid and rising upward. And here is the beautiful intuitive twist. Once boiling starts, extra heat no longer makes the water hotter. It gets spent turning liquid into vapor. In other words, the heat stops raising the temperature and starts paying the escape cost. That is why an open pot can sit there boiling hard, looking more violent and more dramatic, while the water itself stays pinned near 100 degrees Celsius instead of climbing higher. So boiling is like evaporation going full rebellion mode. Normal evaporation is surface molecules escaping one by one. Boiling is liquid water saying, "Forget the front door. We are launching vapor from the inside." And there you have it. Pat yourself in the back. You are an evaporation expert now. If you forget everything we said in this video, remember this one thing. What you're taught in school is vaporation. What you learned here, perhaps for the first time, is evaporation. Vaporation means liquid turning into vapor. Evaporation means liquid turning into vapor and egressing, exiting, going away, free. All a molecule needs for vaporation is to reach the right speed. This is what we call thing one or requirement one. Evaporation requires something to cut the vapor molecule off. Away, free. Think of it like a pair of scissors. You need ventilation to cut the vapor off and away. This is what we call thing two or requirement two. Without ventilation, it won't matter whether it's extreme cold or extreme heat or anything in between. There can be vaporation, but there cannot be evaporation, unless you're in space. Space, or better yet, within a vacuum chamber, is where vaporation and evaporation are one and the same. Why? Because there is no haters team, no team of air vapors blocking them. But this is up to a point, because as you start evaporating molecules, the evaporated ones start to build enough clout around your experiment, which we call pressure. They start blocking the others from evaporating. Here is a toy model to help us understand requirement 2 and why vaporation and evaporation are two different things. Meet one tiny water drop, just chilling on the table. Around it, the air is not empty. The air is in fact never empty. It's a bouncing crowd of gas molecules, plus a few tiny water molecule vapors already floating around. Those fast little air molecules keep bumping the water surface like, "Wake up, buddy, wake up." As a result of these air interface collisions and collisions between liquid water molecules within the water drop, some surface liquid molecules gain enough speed to escape. But wait, above the drop, a few H2O vapor molecules feel this and start crowding the air right above the water drop like some of the most packed-up concert. So some escapees get pushed back into the liquid. Why do they do this? Why are they haters? Well, they don't even think about it. The same thing happens in a highly crowded rock concert. They just do it automatically. Anything pushing to get in gets pushed back mechanically, automatically. Then a tiny breeze shifts just one or two water vapor molecule, say a few molecules away from the water drop and air interface. Boom! The one or two air H2O molecules are pulled or pushed aside along with the one the breeze pushed, freeing one or two seats in the blocking team. One or two ready water molecules find an open spot and jump into the air. And voila! Vapor molecules made it across from the liquid to the air for good. We call our experimental proof a toy model because we can use the faintest of ventilations, and it would still work. Say there is just enough ventilation to push or pull just one vapor molecule. That push or pull motion of only one vapor molecule, sitting a small distance off the rim of your body of water, will give it enough energy and speed to push or pull its neighbors until one of the vapor haters is pulled away from the hater's team, opening up a seat for a new vapor from the liquid water. This is why evaporation happens even in the coldest of winters, because all it takes is the slightest ventilation of even just a very small number of vapor molecules at a time. Here are 5 things you learned today. 1. Every body of water has an invisible part sitting right above. 2. Evaporation requires breakaway speed and ventilation. 3. Every fluid can be mapped, water especially through the Maxwell-Boltzmann distribution curve turned counterclockwise. 4. Because of ventilation, water evaporates from the wings first. 5. As a result, water can be harvested from the wings of any body of water, even along desert beaches. One very beautiful application of this is harvesting water in the desert and in the wilderness. As we explained earlier, it helps to picture water vapor as always forming a kind of invisible presence around liquid water, part of the vapor team which we call haters blocking evaporation, while the lateral sideways team's job is to facilitate evaporation. And these lateral sideways pulling boundaries are the lines along which you can begin to predict the presence of vapor, even in places that look completely dry, even in the desert. And understanding the meaning and power of that sideways pulling line will be extremely important. Now, places like MIT are also working on water harvesting, but their focus is very different from that of the person who wrote the paper that this video is about. MIT is working on better engineering methods to capture water from the air. Integrized Geometry, IG, by Ben Tibola, nicknamed ChibBoss, based on his Integrized Geometry Framework, or IG, is building something different, a science for precise prediction and mapping of where vapor water already is before you even try to capture it. We will unfold that idea little by little in future videos. Integrized Geometry, IG, by Ben Tibola, ChibBoss, is a mathematical framework designed to make many difficult topics in math and physics feel simple, visual, and intuitive, just like in this evaporation video. And in the videos ahead, we will keep doing exactly that. We will take some of the hardest ideas people usually struggle with, ideas from quantum physics, Fourier series, transforms, general relativity, black holes, and much, much more, and explain them in a way that feels so clear, so natural, and so intuitive that both a child between 5 and 8 years old and a university student can genuinely understand them. That is our standard. That is our promise. Our goal is not just to explain science. Our goal is to create new scientists, to awaken the curious mind in you, to bring back the joy of asking questions, to help you feel that deep, quiet excitement that comes when something difficult suddenly becomes simple. And we make a very bold bet with every video. You will not find another place that explains these difficult topics more clearly, more deeply to both young children and university students than on this channel. That is the bet. If we lose it, be among the first 3 to email us proof and you'll get $100. So subscribe, stay with us, and watch the journey unfold. And because this channel is still very new, please support us by liking the video and sharing it with your friends. Your support is the energy that keeps this going as we do this work unpaid, simply for the love of science, for the love of discovery, and for people like you.